Hello everyone, welcome to the solution of LeetCode problem 104 named maximum depth of binary tree. In this problem, we are given a binary tree and we have to return the maximum depth of this tree. Anyways, we have to understand what is the maximum depth. There is a given definition. I am trying to explain it right now. Our maximum depth of binary tree is the number of nodes along the longest path from the root node down to the leaf node. Anyways, the definition might seem a little bit of complex. Now let's understand the definition by using this first example. Here we are given a tree. The root of this binary tree is 3, which has 2 children, which is 9 and 20. And 20 has also 2 children, which is 15 and 7. And the maximum depth of this binary tree is 3 because the longest path from the root 3 to leaf node 7 is 3, 20 and 7. And in this path, it has 3 nodes. So the answer of this example is 3. Anyways, let's understand what is the maximum depth by using another custom example. Here, we are taking a custom binary tree. The root of this binary tree is 9, which has 2 children, which is 8 and 7. 8 has also 2 children, which is 1 and 5. And 1 has 2 children, which is 2 and 3. And root 7 also has 2 children, which is 6 and 4. Now, we have to determine what is the maximum depth of this binary tree. Anyways, according to the definition, the maximum depth of this binary tree is the number of nodes between this node 9 and this node 4. Because this path, which is marked from 9 to 2, is the longest path among all of the paths from the root node to the leaf nodes. And in this path, we have 4 nodes, which is 9, 8, 1, and 2. So in this tree, the depth of this binary tree is 4. Anyways, now let us understand how can we solve this problem. In the technical interview, basically when we are given a tree-related problem, we can apply depth-first search or breadth-first search to encounter this problem. In this problem, we are using the DFS algorithm, which stands for depth-first search. In the depth-first search, at first, we are in the root node, and from the root node, we have to recursively call the callback function into the left subtree and into the right subtree as well. Suppose we are calling the DFS function into the left subtree. Now, our DFS call is presented in node 8. From here, we have to again call the DFS function from the left subtree and from the right subtree as well. Suppose we are calling it into the left subtree. Now, our DFS call is presented in node 1, and from node 1, we have to recursively call the DFS function into its left subtree and into its right subtree as well. Suppose we are calling it into the left subtree, and now we are presented in node 2, which is the leaf node. And from here, we have to return the value. And we have to determine what kind of value we are returning when we reach into the leaf nodes. The value we are returning from the leaf node or from the any kind of node, actually the 1 plus maximum length between its left subtree and its right subtree as well. Suppose in our DFS call, we are presented in node 8, and after exploring all of its descendant, we have to return a value from node 8 to node 9. And actually, what kind of value we are returning? It is the maximum of its left subtree and its right subtree length. Here, the maximum length of its left subtree is 2, because from 8 to 2, it has to cover these 2 paths. And the right subtree size is 1 because it has to cover this path. And when we have completed exploring all of its left and right subtree, we have to return the value of 1 plus maximum of 2 and 1. So in this case, we are returning 3. Now, actually, we are noticing that the maximum depth presented in root 8 is 3 because it is the longest path, and the number of nodes presented in this longest path, which is 8, 1, and 2, is 3. So from 8, actually we have to return 3. Similarly, suppose we are in the node 7, and from node 7, actually we will return 1 plus maximum of its left subtree size, which is 1, and maximum of its right subtree size, which is also 1. So we have to return 1 plus maximum of 1 and 1. So in this case, we have to return 2. Now, when we are applying the DFS call, in one time, after finishing all of the DFS calling, we will be in the root node. And here, the root node 9 is receiving two values, which is 3 and 2 from node 8 and 7. And the maximum depth of this binary tree is the 1 plus maximum of 3 and 2, which is 1 plus 3, that means 4. So finally, our root node 9 will return the value 4. So in this case, we are noticing that the maximum depth of this binary tree is 4. And we have to return the value of 1 plus maximum of left subtree and the right subtree from each node while applying the DFS call. So I hope you understood the recursive algorithm. Now let's move on to the actual solution, our actual code. Here, in this code, we are given a function named maxDepth. The return type of this function is integer, and our presented root has been given as a form of parameter. Now, at first, we are checking if our current root is null or not. If it is, then we have to return 0. Otherwise, we have to recursively call the callback function into the left subtree and into the right subtree. And as each of the DFS call will return us an integer value, so we have to store the value returning from maximum depth function into a variable. For the left subtree, we are storing it into the left variable, and for the right subtree, we are storing it from the right variable. And while applying the maximum depth function or the DFS function into the tree, we have to return 1 plus maximum of the height of the left subtree and the right subtree from each node. And finally, we will find the answer. Now, let's move on to the time and space complexity of this algorithm. In this algorithm, the time complexity is big O of n, where n is the number of nodes. Because in the worst case, while calculating the maximum depth, we have to visit every nodes. And if our tree contain n number of nodes, then the time complexity will definitely become big O of n. And the space complexity of this algorithm is big O of h, where h is the height of the tree. Because in the recursive call, the maximum height of our call stack can be equal to the maximum height of our tree. So here we can see that the space complexity of this program is big O of h. Thank you everyone for watching this video. We will get back soon with another LeetCode solution.